Okay, I just wanted to mention real quick, don't forget that there is the online web lean. If you don't want to mess around with Mathlib getting set up and whatever for the first few episodes, just go on to the online one. It supports the latest version of Mathlib too, so you can use Mathlib with it just fine. And I know the first video on getting set up was pretty brief. You know, as problems come up, we'll be looking at how to fix those. Unfortunately, most of the problems that you get with the build tooling you get because at the beginning you don't really understand how it has its own system of how it works, and once you learn how it works, you stop encountering as many problems, which is not great for teaching because then you can't demonstrate solving those problems. But hopefully you'll learn by example, at least, because I've forgotten a lot of the issues that I had. I just remember that at the beginning I lost quite a lot of time trying to get Mathlib set up. Especially on a slower computer. And especially don't forget with a computer with 8 gigabytes of RAM. If you have less than 16 gigabytes of RAM, you should be scared. Because Mathlib is going to be, you know, if it's 5 gigabytes on disk, it's going to be pretty hefty in RAM. All right, let's get into it. So starting out, of course, this repo is going to be on GitHub under the same name, Intermediate Lean. We're going to have a few different files based on kind of the types. Right now I'm going on types of numbers, so we have naturals, integers, reals, and we're going to be doing inequalities, but then maybe later on some calculus too. We have everything set up here. We have our lean toolchain. We're using the latest version of Mathlib, and we're not pinning the Mathlib version. So I wanted to start with just a very fundamental part of algebra, right? The quadratic equation. Here we have a quadratic equation that goes, a lemma that goes from a quadratic equation to set of possible values. So either x is 2 or negative 2. After we introduce our equation, so that means that now we have access to x squared minus x minus 2 equals 0. We need to somehow apply some kind of lemma that's going to tell us, well, here are the solutions to a quadratic equation. So right away, we're going to start by opening up Moogle. You can do this with Control-Shift-P in Visual Studio Code, or you can go online and type in Moogle. We're just going to do the Visual Studio Code in browser one. Sometimes this one has some 404s that are annoying, but usually it will work to give you an idea. And we're just going to start with the naive approach, right? We're going to type in quadratic and see what comes up. Right away, our first result is discrim, but discrim is a function because it's a def keyword, and I'm not sure how that would help us, right? So we'll go down to the second one, and again, I'm not sure whatever this data set, not sure how that will help us. Quadratic cars for characters, so I don't see much. Oh, but here we find something interesting, right? When is the discriminant when is a quadratic equal to 0? When the discriminant is equal to a square, right? What that means is that if we know that our quadratic is equal to 0, well, then we should be able to say that we have our discriminant equal to this square. So let's start with that. So let's say, we'll start with saying have discrim equals square of, not sure why it's not, oh, there it is. So already what I'm doing here is an important kind of strategy when doing lean with Mathlib. You want to, when you're using theorems that you don't know how to use yet, one of the really good ways to do that is to have statement with the theorem name, and you don't give the have statement a type. Instead, you look at the type, in this case, the type class instance is stuck, so it doesn't know what type this should be. But you're going to gradually apply things to this lemma and see what because if you don't know how to use it, you don't know, you don't know what to give it in what order and whatever, right? So you need to start with something and gradually, tackle the problem, right, in pieces. Some of these lemmas, and one of the reasons I'm starting with the quadratics is because these lemmas are hard to use, especially for, a beginner to lean. At least they were for me. Maybe you'll find them easy. Okay, so we have the discriminant equal quadratic equals 0, but we haven't applied it to anything. Let's look at the lemma. It says it wants a single argument explicitly. So these are implicit arguments up here. It wants one argument, which is the quadratic. So we're going to try to give it our eq, and that did not work. We still have a problem, right? So unfortunately, we have a problem because lean can't decide, most likely cannot decide the type of these numbers. And quadratic equals 0 if, where this discrim equals square, wants some kind of commutative ring, and it cannot just be any kind of number, right? So we'll start by giving this the type real. That did not work. My guess was wrong. So let's try to give, what we want as a type, as an explicit type to our have statement. We know we want the discriminant of 1, -1, and 2, sorry, -2, and then a is 1, x, b is -1. And now we're getting an error under eq, right? So the reason why we're getting an error under eq is because the argument has this type, but it's expected to have this type. Now, obviously, or at least it should be obvious to you, those two things are equal. Those are just, a little bit, this is just a clunky way of writing how you would normally write a quadratic. But lean, the form that this lemma takes is a times x plus b times x plus c equals 0. It does not accept any other kind of form, and the coefficients matter. We cannot ignore the coefficients just because they're 1, for example, or -1. So how do we put the equality into this kind of type, right? Well, we can kind of flip our approach on its head a little bit here, and instead of trying to exactly fit this type, now that we've specified exactly what we want, we can be a lot more loose with our arguments, right? So instead of saying eq here, I could just say, fill it in, right? Maybe that might work. But lean says, okay, we don't know how to do that. We don't know how to do, that much algebra. But maybe we could try something like by ring, right? So by ring nf with eq, something like that might work. Or unfortunately, it did not work. But we could try linearith, and look at that. Linearith worked, and I don't even think linearith needs to be given eq explicitly, right? So what linearith is doing here is it's saying, okay, in order to solve this type, in order to give an equation of this type, using this lemma, and in the second argument where this lemma is going to need something that's going to give this, linearith is determining how to make eq into this format. Right. And so this is a lot easier than trying to do, the more clunky way, which would be something like question mark underscore and, by up here doing more tactics, and then saying refine, and then saying, down here, okay, now we have to solve this. Okay, so we can try to do, ring nf, but now we don't have, this is kind of almost further away from eq. Oh, no, actually, this is very close to eq. So now we can do exact adcom or something with eq. Say using eq. So we could say rewrite add at eq and then exact eq. But in a more, you can imagine that in even in this case, right, this is giving me trouble because, well, actually this is adcom. I'm not going to get into this anymore, but it suffices to say, no pun intended, that this is a harder way of doing it. And you always want to do the optimal approach, right? The optimal approach, if you know what type, then you leverage that and use the general tactics to find it for you. Okay, so now we have our discrim equation. We have our eq equation. A bit of a drawback is that our eq equation is still not in the form that we're using it, because that was determined by linearith but then discarded, right? It's only in here that we have access to that, but that's okay. So now let's search for something in Moogle because maybe discrim can give us the kinds of solutions for a discriminant. So I'm not finding much. If I try exact, I'm sure it won't work. Moogle can be pretty difficult to use sometimes. This would be an example of that, in my opinion. We can try to, look into these definitions a little bit. So what is this definition actually? Oh, it's b squared minus 4ac, right? Okay, that makes sense, but how do we use that? And then in the process of, looking at the discriminant definition, we might see some other useful lemmas, right? So here we have quadratic equals 0 if discrim equals 0. That's not really useful to us. We've already applied something similar. We want the solutions to the quadratic, right? So let's see if we can find something with the solutions. Maybe I'm being silly here. B squared minus 4ac are the solutions, aren't they? Yeah. Yeah, so really what we have to do is unfold the scrim, right? At this. So unfold means to basically get the function's definition and replace the function call with the function's definition. It's like just one unit of computation. So now we have a proper equation, right? So we'll just start by throwing powerful tactics at it, right? So ring NF to get something simpler, and that already looks a lot cleaner. We need to say x squared. Let's see, we have to clear the ones on both sides. So we can say, you know, two ways of doing this. You can do conger arg. So we could say apply conger arg dot minus 1 to subtract 1 from both sides. This is a function that subtracts 1 from a number. We're going to apply it to both sides because both sides are numbers at this. And then we could, you know, do some subtraction, ordering, reordering, because these are real numbers. So we'll just copy this down here. But another way to do it is to use ring NF, take advantage of the power of ring NF a little bit more, right? So instead of saying, you know, ring NF at this, we're going to say we want, I'm being really silly here. This is what happens when you use too many tactics and not enough thinking. So no, unfolding the discriminant doesn't do anything because, right, we're just getting our original equation when we do that. So after some algebra, we're just going to get x squared minus x minus 2. It's definitely not what we want. Let's look up quadratic again. Not much. Wow, okay. At this point, I'm tempted to go look at how I used to do it, because I've done this once before, or twice. Let's look at the library again. So we had quadratic equals if is 0. I'm looking for, you know, an x or x equals this or x equals that. Well, look at that. We have the roots of a quadratic, right? So this is giving us x equals negative b over 2 times a. Which is what we want. And we need to give it the discriminant equal to 0. So we're going to copy this, and then we're going to say, let's go back to the info view. So because this is an if and only if statement, the I want to say tactic, but I would get it. That would be confusing with lean tactics. The strategy of saying we have this and then trying to gradually apply things, it might not work so well. Although this does have hypotheses, so it'll still work. It'll just be maybe a little clunky. I mean, this is clunky to begin with, so maybe not. So we're gonna put in some holes for these things that I don't really care about, like a not equal to 0. What I really want to do is I want to use this, which is our discrim equals 0, but now I'm seeing that it's not equal to 0. So we need to say, okay, so maybe we do need to do some unfolding. Wow. Okay, discrim. No, but if we unfold the discrim, we're not going to get discrim equals 0. So what we need to do then is say we have to show the discriminants equal to x squared minus x minus 1. So that just means expanding out the right side to get x squared minus x equal minus 2, right? So we have to show that we need to show that this is equal to, and then we have to use x squared minus x minus 2 because we know that is equal to 0. By the transitive property, we will have the quadratic, the discriminant equal to 0 because this is equal to this, which is equal to 0. So first we have to show this equality. And of course, we're going to try to use ring at the beginning, see if ring works. Ring does not work. The reason why ring isn't doing anything here is because it can't break the square. So what we need to do is we need to apply a lemma that says square equals, you know, like square add or something for the addition inside a square. So let's see if there's a square add. Square add square mul, square add mul square, add square. Add square is probably for, oh, okay, now that worked. And now ring, we're getting x squared times 4. That can't be right. Wait a minute, what's going on here? Did I copy this in wrong? Okay, we have the discriminants equal to 2 times x plus negative 1 squared. X squared minus x minus 2. Huh, so we're still going to get, oh, I see, we're going to get a factor of 3, I think, and then that's going to reduce to a factor of 1. Oh, maybe. We'll see, we'll see. Okay, let's do some algebra here. First of all, we're going to try omega. Omega doesn't work. Oh, and actually, sometimes even better than linear combination is... Sorry, than ring is a linear combination, but it doesn't look like it. Okay, so ring NF, we're going to show... We want to show that we can subtract x squared from both sides. So we'll do that with conger arg. Oh, sorry, we can't use conger arg here because that is for, conger arg is only for hypotheses or goals where the form is f of x equals f. So what can we do here? Well, let's just make sure that we're not trying to do the impossible real quick. So we have 1 minus 4x plus 4x squared equals negative 2 minus x plus x squared. So get rid of this on one side. This becomes a 3. Add x to both sides. This becomes a 3. Add 2 on both sides. This becomes a 3. And then this becomes 1. This becomes 1. This becomes 1, which is not what we had. What's going on? Okay, that's confusing. Yeah, this is what I thought. I mean, we would have a 1 left over. Huh, did I do something wrong here? What? 2 times 1 times x plus negative 1. Squared. See, I never learned algebra this way. I did not learn it by using discriminants. I learned it with like the square method or whatever. That is the problem. I'm not a mathematician. Of course, these two things aren't equal because they're not equal. So just because we have a chance to use the transitive property mean we have to, that doesn't mean we're allowed to use it, right? So this is not true. Okay. So what is true then? Well, let's at least put this into a form that we can recognize, right? A bit more, a little bit easier to use this, right? So let's try linear combination. Doesn't work. Ring, and so I think we can do conger here because we have the negative 1, negative 1. No, that's not the same argument, right? Because that's not equal to 0. Instead, it's equal to 1 times 4 for both. I like to write it with the little star with no spaces. Makes it a little bit easier to read. But let's see if this helps us. We still need as our goal to satisfy quadratic equals 0 if of discrim equals 0, which takes a discrim equals 0. Maybe we're going about this the wrong way, right? Let's go back to the library and say, when does the discrim equal 0? Well, the discrim equals 0 if there is a unique x such that a times x plus b x plus c equals 0. Okay, we could use that. Seems a little weird to use that because we would be using the goal. In other words, 2 and negative 2, we would be plugging those in. Oh, okay, this is better. I was doing the wrong one. So yeah, maybe it would help if we started with the correct lemma, right? Not just some random equals 0. This is my problem when I do lean. All right, quadratic equals 0. It's always important to know what there should be in the library. All right, and here we have our x equals negative b minus s over 2a, which is exactly what we want. This is the quadratic formula. We just need to apply it to our discriminant, and our discriminant needs to be in the form of a square, which it is because of this. We don't even need, sorry, not because of that, because of discrim equals square of quadratic equals 0. So now we apply quadratic equals 0 if we have, let's get rid of this, quadratic equals 0 if we need to apply a not equals 0. Then we need to apply, so x is h is this, and then x type. And we get an error is expected to have type that. Okay, so the problem here is that our discrim is in the form of squaring where it should be multiplying. Not sure why they have different, like sometimes they use squares, sometimes they use self-mul. Is it self-mul? Mul self? I think it's actually just square, isn't it? Yeah. Okay. So now we just need to show in our whole that 1 is not equal to 0. That we can do by simp or linearith. Simp is less powerful, so I'm using simp because I know it works too. So, well, simp can be more powerful, depends. Less computational, I would say. Okay, so now we have this monstrosity. And I think omega can do this. No. Okay, fine. Maybe we have to simplify a bit, and we get true or. Oh, that's weird. That should have been simplified. We do norm num maybe. Norm num can work better for these. Yeah. So norm num is better with the logic ring is just for numbers. But now we're back to where we started. Not good. That is not good. We need to, this is an if and only if statement, right? It's an if and only if from an equation of this form to the solutions, which means we need to rewrite this at eq. But that's not going to work because, oops, we need to rewrite this at eq, but it won't work because eq is not of this form, right? So remember when up here we did the whole linearith thing to put it into this form? We actually are going to need that later. So instead we're going to say case eq with this type by linearith. And that way we have access to the new eq, right, later on. And it will work with the rewrite here. Rewrite this at eq, where eq is in the same form 1 times. Basically, all the coefficients are explicitly labeled, right? And we're using addition instead of subtraction of positive numbers, right? Okay, so after we do that, now we have we should have an or. How come we don't have an or? Oh, the or is at eq, right? And we no longer need this. So I'm just going to copy this all into here, because we're only going to use it once. And now we have cases on eq, right? So cases eq. And we'll try omega for both of them. Omega does not work. Let's see what we're working with here. In the first and second case, first case we have to show, first case we have positive, in the second case we have negative. Okay. Okay, so I think this is just linearith or something, right? I'm surprised omega can't do it. I'm surprised linearith can't do it. Oh, because we're not doing it at this. So we have to say norm num at this, right? Okay. So now we get 2x plus -1 times 2x plus -1. So if x is equal to, we need to use our cases here with odds net, right? So instead of this, it's going to be positive. Whoops. Where is the equation for x? Oh, shoot. Why did that simplify to true? I don't want that to simplify to true. It should simplify to x equals 2. No, it does simplify to x equals x, doesn't it? Okay, but I have the roots. Oh, these are equations for x. Why does it give it to me in this form? It's so weird. X is equal to -b plus s over 2 times. Okay, but the discriminant is what? Back to the library we go. Oh, this, this is good. This is what we'll need for the second one. Okay. Also need to show not exist square, I think. Which now that I think about it might make this one easier to use. We'll see. Okay, but focus. So we have to give something to the discriminant that is not equal to, that does not include x, right? Otherwise we're just going to get the same thing back. What if we rewrite, can we rewrite this with the discriminant maybe? X is equal to the negative discrim. Let's see here. Well, first of all, what do we get when we unfold discrim at this? What does this give us? We have the unfolded discriminant is the -1 squared minus 4 times, yeah, so this is b squared minus 4ac. The quadratic formula says, quadratic formula is for -b over 2a though, which is what quadratic equals 0 if gives us. In other words, we need an equation for s. So this is s. If this is s squared, oh, I see. We need to put this into the form of a square maybe? Well, it's 1 minus 4 minus 2. No, it's 1 minus 8, right? No, it is 1. Gosh, I can't do math. Okay. We have 9 is equal to s squared, where s is this thing, right? So we have 9, which is 3 times 3, is equal to this squared. Okay, so it's ring NF is doing the right-hand side too, and I don't want that, so we're going to add a convert left-hand side in front of it. And then we have to also say tactic because what? Convert, oh, sorry, convert at this left-hand side. We get 9, and now we have 9 equals the square of that. Instead of doing mul by square or whatever, we'll just say this because we're going to use it anyways. Okay, now what's the problem? Okay, so now we have our s squared equals some number, but we need to say that this is a square too. Yeah, that also doesn't work. Okay, finally. Okay, linearith can do that. Good. I don't know why linearith couldn't do it the first time. Oh, because I didn't have the type equals. Okay, good, good. So now we have a square, and oh, so maybe even better is we have an equation for s, right? So s is equal to 3, and this takes more than what linearith can do in one step, huh? Okay. Okay, so let's undo some stuff here. Let's say this is a square. And we'll say this is a square, and then we're going to show that we have 3 equals this by exact. So this is a great time to use library search because non-trivial equality squares aren't very easy to do with. I mean, the tactics don't really like squares that much. So there's probably a lemma that says, you know, a squared equals b squared, then a equals b. But that's not actually true because of negative numbers. So we actually need to say the absolute value of both sides. The absolute value of 3 is equal to the absolute value of this. Now we get this. Exact works. Okay, so now we basically have the cases of the positive and negative s, right? This is looking a lot better. We have an absolute value expression, and we have 2 cases where that absolute value expression is equal to positive and negative, right? But this is still something that's hard to work with in Lean, right? This is still cumbersome. It's not trivial to say, you know, well, okay, you have this absolute value, you have this the positive, negative. I don't even know where they went. Oh, they're up here now. Put them together and get x equals 2, right? No, can't do that. So let's try it though, because you know, you never know, right? Let's try some magic here. Let's see if Aesop can do it. Nope. Aesop does give us this, which is actually, sorry, we're actually done at this point. I don't know how that happened, but this is, yeah, we didn't need to do much else, did we? Why did we not need to use quadratic equals 0 if? Sorry, and shouldn't linearith be able to do this too? Is it because we have the absolute value of 3? Okay, first of all, the absolute value of 3 is 3, so we'll just make this a have. A lot of times when you have something so close, you know, you can just say simp with this, or simp a using this. That works. Or even exact. We can do exact again, you know? So we convert the first exact to a have statement, then we use a second exact using it. In this case, that doesn't work though. We could even go one step further. I mean, this is just being super nitpicky, but we could say have 3 equals 3 by refl. So we need to start labeling things. We have this. We want to replace the previous one because we don't care about this square one. But we don't want to replace this one. We have discrim eq. Change that. Change this. And now at the end, we have to show. So we don't even need, once we use discrim eq, we don't even need it, which is interesting. I wonder if we even need to rewrite this. Wow, we don't even need to, oh, interesting, okay. Okay, so let's leave that commented because it's for this. Instead of using replace here, we're going to say have, and we're going to organize things a bit better. So this is part of this lemma, so we're going to put it inside this lemma. And now we just need to solve this equation 3 equals the absolute value, right? So now finally we do cases with this. I'm still, like, my mind is not accepting that we didn't need to use quadratic equals 0 if discrim equals square of quadratic. I guess that discrim is, this does everything we need. So now we have positive and negative cases. We need to actually do cases on the absolute value of 2 times 1 times x plus 1. This requires a parentheses. And then in both cases, right, first of all, I want to check linearith doesn't work here. Okay, linearith worked. So unfortunately, we don't even need to do the ABS cases, but for the sake of example, if you needed to do more algebra and linearith wasn't able to solve it in one go, you would do this. You would have your 2 cases, and then in each case you would solve the positive and negative versions, right? So in this first case, let's get rid of this. In the first case, we have you're given an equation and an inequality, right? So you're given 2 things, that the absolute value equals the positive or negative value in either case, right? In the negative case, it's equal to the negative value. And then you're also given that that value is less than or greater than 0. So sometimes what you want to do is you want to pattern match on that equality, right? So there's a GT 0 here, and then there's a less than 0 here. I was actually wrong. We're gonna need a good way of doing this. I have to type it in again. Ugh. Space. So typically we rewrite the absolute value equation everywhere to get rid of it. Another way of doing this, more powerful way, is just to say simple, and that gets rid of the unnecessary hypotheses too. Now we have the positivity, and oh, it rewrote my pos equation into an inequality, which is interesting. Okay, so now we have to show x is 2 or -2. We can show x is 2 by saying, what? Linarith can't do this? Let's try norm num it. Let's see what we got. Not much. I don't want to have to do... I'm confused as to why I need to do another case of absolute value. This is strange. What did we start with? We started with this, but I did absolute value cases. I should have... did simp all... I think simp all... Okay, that's interesting. So simp all, what simp all did was it simplified this, the 1 times x, first, and then when it tried to rewrite the positive equation, it couldn't because this had already been simplified a little bit. This had already been changed a little bit. So we actually want to be more surgical here, and we want to say rewrite pos. The first way I did it at star to get that equation. Why did that still not work? We should be... Okay, this should be rewriting at this because we should know... What? Wait a minute. Why is this -1? Oh, I forgot the -1. That's why. Yeah. Okay. So now simp all should probably work better because usually simp all doesn't do what you don't want it to do. No, it did what I didn't want it to do. Okay. Never mind. Now if I do simp all. Okay. Now if I do simp all, we get, you know, we get what we expected. Okay. So we don't need to do simp all here though. And we don't need it. This is a perfect example of linear combination. Linear combination at this divided by 2. Okay, maybe it's not, but we at least have x equals 2. Why? Really? Oh, maybe this is the -2 one. Nope, I don't like doing math. So we have add 2. This is a +2 case. We need to simplify at this divided by 2. Fine, we'll do conger arg. Cancel that 1. It still doesn't work? Is it because we need to say 2 equals x? Oh my god, linear combination. Come on, that's pathetic. Can't even do symmetry? Okay, so you can do the +1 and then divide everything and do all the algebra, but you can't do symmetry? Okay, good to know. Exact, of course, can do this. That's crazy. I'm not doing that. We're going to do Linarith or Omega. Can't believe it. Can't believe Omega can't do this. Come on. Okay, come on. We're going to be super fancy here. We're going to say by sim. Does this even work? Is this even valid syntax? No, it's not. Okay. You can use equalities inside rewrites and simp by saying like, you know, .sim or whatever. We could have said equal sim of this, but this is easier. Do I really want to copy and paste this proof? I wonder if you could do, I don't think you could do, I was going to say, I wonder if you could do without loss of generality here, but I don't think you can. No, actually you might be able to because you have 2 equations inside absolute values. Without loss of generality, 3 is equal to whatever. I always have to complicate things. Just copy and paste the proof. So we can at least be a little bit fancy and say substitute, or can we? Okay, this negative case is a little bit trickier. So after rewriting neg at this, we get this expression. Let's do some bit of pre-processing here. Norm num at this, and now we have linear combination. So let's try like omega or something instead of linear combination. We can even try ASOP. Let's use our trusty conger arg. We're going to do the other side this time. So we're going to do -1 plus so that they're next to each other at this. Now we get that add com. Add associative at this to get that 1 plus out of parentheses. Might have to do this on the left side. Nope, that works. Okay, norm num instead of rewrite to do it all in one step. We get that. This should be Linarith. Okay, fine. Linear combination. It's not true. What? Oh my god, I can't do basic algebra. X is equal to 1? -1? Oh my god, it's true. Oh, that's embarrassing. Okay, so this is actually -1 up here. Wow, okay, does Linarith do the whole goal then? No way, right? No, okay, good. I was scared. Okay, wow. No wonder it didn't work. You even need that? Yeah, you do. Okay, so negative this. So linear combination here is taking this being this equation, multiplying everything by -1, dividing everything by 2 to get -1 equals x. And we're simplifying. What did we learn? You don't need to use quadratic equals 0 if you already have a quadratic equal to 0, you just take the discrim using discrim equals square of quadratic equals 0. We had a square of 3. I don't even know where we got 3 from. But okay, I guess that's the b squared. So if we used different numbers, I don't think we would have gotten lucky and gotten 3 squared. Honestly, this is weird. Do not understand.